Hello and welcome to this episode of T-Tech. On today's episode, we're going to discuss the basics of IP addresses. I do hope you enjoy this one, and let's get into it. Hello and welcome to this episode of T-Tech. So on today's episode, we're talking about IP address basics. So in IP addressing, there is two types. There's IPv4 and IPv6. Now, IPv4 works at layer 3, and that is the network layer of the OSI model. And its job is it identifies a single device, so a single computer, anything that can be connected to the internet. And a very important thing, it's a logical address, meaning where it physically is doesn't matter. It can move around, and it still will identify something. Okay? Now, with IPv4, this is 32 bits long, and it's binary bits, so ones and zeros, and that is how long that is. But we don't see them as bits like that. We represent them in decimal when we write them out, or see them on a device. And a very important concept is making networks with IP addresses. So to do this with IPv4, we use Subnet Masks, and that will group the devices together. Now, IPv6 is very similar, and the reason we are starting to use IPv6 more is we have a need for more IP addresses that are unique than we currently have at the moment. But again, it works at layer 3, and it identifies a single device. Now, there is times where they can identify multiple at a time, but that's something different. We're not getting into that here. And it is a logical address again. Now, a difference is it is 128 bits in length. So this does mean, though, there's more values that can be used with this address, this type of address. Okay? And instead of decimal, we represent it in hexadecimal, even though it's still binary bits underneath it. And again, we still want to make groups of devices. That's very important in networking. So instead of the subnet mask, we use the prefix length to make those groups. So, starting in IPv4, this is the structure of it. Now, how we said it's 32 bits, and those bits are in sections or octets. And up here, what we actually see, we see 192.168.1.1. Now, those are really 8-bit chunks. And down below here, we see what computers actually see, which is the binary. Now, how do we take the binary and use and see the decimal? Well, in each of those sections, or a byte in other words, because it's 8 bits, there is bit values that are decimal. And very simply, in this byte or octet, I have the first 2 bits on here. So what I do is I take 128, and then I take 64, because those are the bit values for each of the bits here, and I take those and I add them together. And when I add them together, I get 192. So then you just take that and put that in a section. Likewise, this is the equivalent of 168, so we would just add up the bits for that. Same thing with the last 2 sections of this address. In this case, the bit value here is 1. So we just take 1 and put it there. We don't have to add anything. Now, the other thing is these are powers of 2, and they double by powers of 2. So it goes 1, 2, 4, 8, 16, 32, 64, and 128. and that adds up to a maximum of 255. All right, so 255. So that is how computers see them and how we represent them. And it's very important that you know how to convert them like that. All right? So before we get into actually how we make the groups with the subnet mask, we have to talk about address classes. Now, with address classes in IPv4, what determines what class we have is that first octet or first section. So our classes, class A is 1 through 127. Class B is 128 through 191. Class C is 192 through 223. Class D is 224 through 239. Class E is 240 through 255. So, with these classes, basically before we go into the subnetting part, what you have to understand is, depending on the class of IPv4 address you are using, that determines how many networks you can create. Okay? So how many networks you can basically slice up. And the thing to remember is, with the class A here, we have 8 network bits. All right, so 8 of those 32 bits are network. That means we can create more groups. Okay? The less network bits we have, it basically means the less networks we can create out of that. So in other words, class A, we can create lots of smaller networks with a class A, whereas with class C, we can only create so many of those networks called subnetworks or subnets. Okay, so this is our same address as before. And they're still binary, all right? So the whole thing of what a subnet mask does for us, we have our whole 32 bits. All the subnet mask does is separates those bits up either into a network portion of the address or into the host portion of the address. Okay? So in our example here, what you see is a 24-bit subnet mask. And as we said with the bit values, adding up to 255, the maximum value when we see it in decimal is going to be 255.255.255.0. Okay? And that you have to have them all on from left to right, and they can't be on and off in any other pattern. They all have to be on. Okay. Excuse me. And basically, though, this is 8, 16, and 24. So when we actually look at our address, what we're saying is the first 3 sections, or 24 bits, belong to the network, and we can't change them. That's why they're in red here. We can't change them. This host portion in the green is 8 bits because in the mask, these are all zeros. So that's the part where we actually can put a value, have a computer on this network. Okay, those are where the unique values will come from. Now, something important about this subnet mask is you have classful subnetting and classless subnetting. But with classful here, we subnet where we would appear on the classes. We only subnet as 8, 16, or 24. And then this 24-bit subnet mask is an example of that. But if we want to go starting with this mask and borrow a bit, So 25 now, because 25 bits are in the subnet mask. Our mask is now 255, 255, 255, 128. And of course it's that because we add the bit value in. That is 128 there. And that changes things a little bit. This is where it gets a little confusing. But basically, with a subnet mask, when you create the networks, the last bit that's on in that mask, you remember the bit values, okay? The last bit that's on is the value your network counts by, or your block size. So basically, in this network, you take that and then you have a network ID. In ours is 192.168.1.0 here. And we would count all the way from, in the third part of it, we would count by 1. So that would actually give us 2. So 192.168.2.0. And what we find out is, in between 192.168.1.0 and 192.168.2.0, there is a few important things. You have the network ID, and this identifies the network. Then you have the valid range. This range, in this case, the 192.168.1.1 through 192.168.1.254, those are what you can assign to the PCs in that network. Okay? And the broadcast address is when you want to talk to all the PCs in the network. The 192.168.1.255. And that range here, you can only use the valid range here. Okay? You cannot use the network ID, and you cannot use the broadcast address. Those are reserved. Now, the part where it gets a little confusing is when you're borrowing bits from the host portion. Because now we're borrowing 1 bit. What's confusing about it is we still are going to see the same values, but just in a different way. So with 192.168.1.0, we have now we have 25 bits of that. So here we're actually going into this last section, and then this bit is part of the mask. So remember what I said about the bit value, the last bit on in the mask? Whatever that bit value is, that's what your networks count by or increment by. And that's called the block size. This one is 128. So now, our network ID still starts at 192.168.1.0. But we count by 128 in this last section. So our next network is 192.168.1.128. Okay? So with that being 128, one less than that is the broadcast address of the network. So our broadcast is 192.168.1.127. And our network ID again is as before. But this time our range is actually less addresses. So we only have 192.168.1.1 through 192.168.1.26. Okay? In other words, the less host bits you have, the less computers you can have in a group, or a subnet, in other words. So if we put all this together, we have one group here, and now hopefully we understand that those fall in the valid range. And then this is called CIDR when you see the number. It just means we talk about the subnet mask in terms of how many bits are on, instead of writing it out in decimal, but you need to know both ways, though. But anyway, we have the 1.0 network and the 2.0 network. And because these are on two separate networks, the computers in this network don't know about the computers in this one, and vice versa. So they need a router to connect them. And that router actually has an IP address on both of these networks. So it has 192.168.1.1 1.1 on this network, and 192.168.2.1 on this network. So when .2 wants to talk to this .3 over here, even though the host ID, the host portion looks the same, it's not, because they're on the different networks. So it would go ahead and send to its router here and send it over, and vice versa. So now we're into IPv6. So the structure here, it's somewhat similar, but it's represented, as we said, in hexadecimal. Now, what that means is it basically is a way to group more bits in less space to actually represent them. So the the first part, 2607, that's actually representing 16 bits, but with only 4 characters. Okay. The thing with IPv6 is you still have a network portion here, the network prefix, and you still have the interface ID. Now, the interface ID is a lot like the host part of IPv4, and the network portion is just like our network. Okay? Very important to understand here. The first part of an IPv6 address is called the registry portion. So this is like Aaron for America for assigning the addresses. And that's where that's what the first section represents, and that's the first 16 bits. But when you keep going over, the next part represents the ISP, the service provider, and they were assigned that by the registry. Okay? The next part is the company. And the final part, in the network part at least, is the subnet ID. Okay, or just like this subnet part. Now the last 64 bits there, or 4 sections, is the interface ID, and of course that identifies the computer. This part, all the way up to 0802, is the network. So we would say this computer is on the 2607, etc. 0802 network. Okay, it's a lot bigger. There's a lot more. But then that would represent them. Now here, as you see, we have a lot of zeros, and it's a big address. What we do when we represent IPv6 is there is rules to compress it. And I'm very glad there's rules to compress it. It makes it easier to deal with. There's 2 main rules. There is leading zero compression, and there is a way you can compress it by using a double colon in the address. Leading zero compression just means in any section, we can take out any section that starts with zeros, we can take those zeros out. So up here, in the subnet part, it says 0802. I took that 0 out there. And in that section with the compressed version, it's just 802. Okay? In this section, where it's 3 sections of zeros, since those are all zeros and we know that, we have the ability to represent them all by this. They're truncated, is what it's called. So they're basically just put in there in between the double colon to shorten it. And anyway, when we reverse this process, the first thing you want to do is put the zeros back that you know are gone. Okay, so we'd put that one back to 0802 because we know that it has to be a 0 there. And then what you do after that is count how many sections you have. And you're supposed to have 8 sections. So what you would do is, like here, if we're still missing the 3 sections, but I would put the 0 back in. I would count 1, 2, 3, 4, 5. I'm supposed to have 8. So then I know I have 3 more groups in there of all zeros. So then I know what to put in place at the double colon. I hope that made sense. But the computers are still seeing the the bytes. Okay, in this case, a lot of them, so I couldn't write all the ones and zeros, but they're still seeing that. But with hexadecimal, when you're dealing with it, you have to understand you're not going 8 bits at a time, you're using 4 bits at a time. Okay? So we only have 4-bit values, but they're still the same as previous, as we just talked about. So they're 1, 2, 4, 8. So your maximum value is 15, and that lines up with how hexadecimal their values are 0 through 9, and then when we want to go into 10 through 15, we actually substitute the letters. So we substitute the letters A through F to mean 10, 11 is B, 12 is C, etc. And F is the maximum. So what we do here to turn it into the hexadecimal is we take this here, we add those values up. So 8 plus 4 plus 2 is 14. And then that gets us from the binary into decimal. And then we know in hexadecimal, 14 is E. So that is the representation for IPv6. And that's representation of the E over there. That's what the E really is. Okay? Now, the last thing we need to talk about in IPv6 is how we can use the Subnet Id to make more networks. Now, it's 16 bits, so you can have up to 65,536 subnets, okay, for each section here. So with the prefix length, remember the Subnet ID is 16 bits, so we have 4 bits here, 8, 12, and 16. And this is still the portions we discussed for the network, all the way up to the last one there before the interface ID. And what we're showing here is the /:/56. What this is focusing on is the Subnet ID portion, and this means 56 bits of this address are the network. Every other bit is assigned to a host, is assignable to a host to identify a computer. So when we get up to here, so we have 16, 32, 48. Then we start counting 49, 50, 51, 52, 53, 54, 55, and 56. And we're in the Subnet ID portion. Now think back to the IPv4 subnetting. We just look at that bit value, and that's where we count from. So from here, it's actually the bit value is 1. In this section, if we go back, we're right here, that bit value is 1. So in each one of these are representing one piece of this. So the bit here is this 0, okay? And because that is 1, we count by 1. So to bring it together, if we subnetted with this prefix length, we have 2001, 2600, 2000, 1000 / 56 on this side of the router. And we still have our devices. And what we'd do to go into the next network is we would have 2001, 2600, 2000, 1100, because we incremented by 1 in the Subnet ID portion. So that is the other IPv6 network. Now the router, how you would say this, its address is 2001, 2600, 2000, 1000, ::1. Now there isn't actually 4 double colons. I just put the double colon down there so you understood it was IPv6. But that's ::1. And then this would be ::2, ::3, ::4, and they're all in this 1000 network. Again, they don't know about the hosts here. They can't see each other directly anyway, so they have to use a router, but the router is now using IPv6. It still has an address in each of these networks like before, and it routes between them. And in IPv4 or in IPv6, the router just uses the destination address in the packet. And it just compares that with its routing table and sends it on its way. But with that, that's the basics of what IPv4 and IPv6 addressing is. This is very crucial to computer networking. I'm Tyler with T-Tech, and have a very nice day.